Okay, good morning, everyone. Today, Andrew Snowden from Michigan will tell us about measures on combinatorial objects.
Oh, thank you. Thanks for the invitation. It's great to be here. I should say right away that all the main ideas start her with Nate Harman. So let me start by giving some motivation or kind of a general overview of what's going to happen. So if we have an algebraic group, we can look at its category of finite dimensional representation. And this is a nice abelian category that has a tensor product. And kind of the main goal for what we're doing is we're trying to kind of understand tensor categories like this. So maybe a first goal is to just construct examples of tensor categories. So let me put the technical word here. So the class of tensor categories we're talking about is are called pre-Tenochian tensor categories. So I won't say the full definition right now, but the key points in pre-Tenochian is that the category should be abelian. The object should have finite length. You should have a tensor product, and every object should have a dual. And having duals is really, really important. The Tenochian reconstruction theorem essentially says that if you have any tensor category in this sense, where the objects have underlying vector spaces which are finite dimensional, then you're just of this form, and so you don't find a new example. So if you want genuinely new examples, you somehow have to construct a situation where things are behaving like finite dimensional vector spaces, but there aren't finite dimensional vector spaces, and that's very challenging to do. So one of the first examples is due to Deline. And he made this category that's called rep ST. So the S here is the symmetric group. T here is a complex number. And the underline is to indicate that this is not really a category of classical representations. It's some abstract category. And the idea is that this sort of interpolates the representation categories of Sn for all n. And what that means is a little bit subtle. The kind of quickest construction of this category is you can obtain it by taking the ultra product of the rep Sn categories. So that category is actually huge, and this will be a subcategory of it. So subcategory of ultra product. This isn't really the most aesthetically appealing construction because it depends on a choice of ultra product, and it's a big transcendental construction. And there are kind of better constructions known, but I think this is the most efficient or quickest way to say the definition. And you can do this same idea with other sequences of finite groups. So this is based on taking the sequence S1, S3, etc. And for other sequences of finite groups, this also works. So for instance, you can sort of interpolate the finite general length groups, like a rep GLT FQ category as well. And there's some other examples.
What is ultra product?
It's a construction based on an ultra filter. So if you have some family of sets, you first take the ordinary product, and you can think of an element here as like a sequence of things, right? Where the ith thing is an xi, and then you put an equivalence relation here, where you say that two sequences agree if they kind of if the set of indices at which they agree belongs to this ultra filter, which is some family of subsets. So the way to think of it is like you have I, which you can think of as some kind of space, and kind of an ultra filter. So if you choose an index, you can look at all the subsets that contain that index, and that's an example of an ultra filter. But a general ultra filter is something that looks like that but doesn't come from a point. So it's like sort of picking out a point, an imaginary point that's not really in your set. It's a very cool construction. You should know.
What does T come in the
That's a good question. So here we're taking the ultra product of these categories, let's say over the complex numbers. We're looking over rep C. And this end result will be a category over the ultra product of C's. So if you call C star the ultra product, or really ultra power of C, That's really the coefficient field for this category. And the T is kind of like the dimension of the basic representation. So for rep Sn, the basic representation is Cn, and that has dimension n. And so T will be sort of the element of C star represented by the sequence of those things. It's like the ultra limit of the dimensions. And that's a transcendental number. It's transcendental over Q. But you can get algebraic numbers if you use finite fields instead of C. Choose your ultrafilter wisely and stuff. So there's a lot of flexibility. Any other questions? Okay. So now then gave some kind of a more general construction, not based on ultraproducts. So he gave a construction of tensor categories, sort of based on regular categories, with something called a degree function. And the details here aren't very important, but you should think of this regular category in his construction as some kind of combinatorial information. So for like this category, the regular category would be finite dimensional FQ vector spaces, which is kind of a combinatorial thing. And then the degree function is some kind of numerical thing on that combinatorics, which is giving you these parameters. And a lot of these interpolation categories fit into his setup. Some don't. And then there's some categories that aren't interpolation categories that also fit in the setup. So it's not a complete containment one way or the other. And so what Nate and I were trying to do initially is we just wanted to understand this category better, the classical kind of rep ST category. And we wanted to understand it in more kind of classical representation theoretic terms. All these constructions are like pretty categorical in nature. And we wanted to say it's kind of representations of some object. And the object that we settled on was it should be connected to the infinite symmetric group. Sort of makes sense because you're taking a limit of finite symmetric groups. And well, once you get at the infinite symmetric group, you still need to explain where this T is coming from. And we thought about it for a while and came up with this idea of what we call a measure. And that kind of explains the parameter. So our construction is that you start with a group. So in the rep ST case, you start with S infinity. And then we realize that this works for a broader class of groups called oligomorphic groups. So it's going to be an oligomorphic group, which I will define at some point, plus one of our measures. And this is going to give you a tensor. So here I'm using tensor category with kind of a loose sense. You don't always get one of these nice pre-Tanakian categories. You get something. So these oligomorphic groups are kind of infinite permutation groups. So they can be a little intangible. They can be quite complicated and hard to get your hands on. But fortunately, they all come from finite combinatorics. So these oligomorphic groups kind of correspond to combinatorial things called Frisé classes. And you can see the measures in terms of this finite combinatorics. So for developing our general theory of tensor categories, like using these groups is more convenient. It leads to kind of just a nicer abstract theory. But whenever you want to do an actual example, you need to get your hands dirty with combinatorics, and it's more convenient to go to these finite objects. And so, yeah, it's just some kind of like finite combinatorial data plus some numerical data gives you this tensor category. And yeah, it actually looks in a way quite similar to Knopf's setup because it's like some finite combinatorial data plus some numerical data, but the details are different, and we see some examples that Knopf doesn't. Gives you a different theory. So in the first part of the talk, I want to explain just kind of the finite combinatorial situation. So I want to tell you what Frisé classes are and what our measures are in terms of this point of view, and give you a bunch of examples. Okay, so that's the. So let me fix a tuple of positive integers. This is going to be called the signature for what we're doing. And then a structure kind of relative to this sigma is just a set together with relations for each one of these ends, and the ends tell you the arity of the relation. So with subsets, let's say R alpha inside of X to the N alpha. Okay, so if you just have one N, if R is 1 and like N1 is 2, we're just looking at a set with a binary relation. And there's lots of things you can model with a set with a binary relation. You could be thinking about orders, partial orders, total orders, or maybe graphs, directed graphs, undirected graphs. So this is like a very flexible setup. Yeah, and an embedding of structures. Is an injection such that the relations pull back to the relations. Just write it this way. So if you're thinking about graphs, an embedding of graphs from this point of view will be like an induced subgraph. You have a set of vertices, and then you just take the edges in the ambient graph and restrict down. So that's what I mean. And then like a really important concept throughout this whole thing is the idea of an amalgamation, which maybe you can just guess based on the word. It's some kind of gluing. So if I have embeddings of structures like this, but given this setup, an amalgamation is a way of gluing y and x prime over x. So I'm going to describe this formally in the following way. It's as a structure y prime with embeddings of y and x prime. So let me call these I and j. I prime going from the x prime to y prime, and j prime from the y prime, such that the diagram commutes. And these maps are jointly surjective. So y prime is the union of the images. And this is not like a push-out square. In most situations, there will be many choices of amalgamations, and there's no universal property. I'll do an example of an amalgamation at some point soon. Okay. Okay, so now I can tell you what a Frisé class is. So it's a class of structures with a fixed signature, such that, first of all, if you have some structure in your class, I'm going to call the class F. So if you have some X in your F, and if you have some substructure of X, that implies that that substructure is in the class. People say the class is hereditary. It's closed under going to any substructures. The kind of really important condition is called the amalgamation condition, which means that whenever you're given a situation like this, so given embeddings like this, where the three initial things belong to F, then you can find at least one amalgamation that belongs to your class. And then finally is just the finiteness condition. There should be finitely many n element structures in that isomorphism. And actually, with the way that I've set things up here, if you have a finite signature, there's just finitely many n element structures in the world up to isomorphism. So this is kind of automatic. But this situation makes sense with infinite signature, and then C is actually a real condition. Okay, any questions? What?
Where does the name come from?
A guy named Frisé. Roland Frisé, maybe? He did this important construction, which I'll tell you about, called the Frisé limit. There's a way to take a limit. I think it was around 1950 something.
What does this symbol mean? I,
Where?
the image.
Oh, union, that's, it's a union. Sorry.
Oh, also it's not finite here.
What?
X is always finite.
Oh, yeah, I should say that, thank you. It's a class of finite structures.
They will have the same signature in the.
All of the same signature, yes. Yeah, thank you. Any more questions? There's lots and lots of examples of first-set classes. So for instance, finite totally ordered sets or finite partially ordered sets or graphs or trees, do directed graphs, undirected graphs. There's just tons of examples. All right, so now let me tell you what measure is on a first-set class. And I'm going to put the definition here so I can leave it up for a while. So a measure mu on a class F is a rule which attaches to every embedding of structures in F a number. So I goes to U of I. Where I is embedding. Such that three conditions hold. So the first two are pretty easy. One is that if you plug in an isomorphism, which is number one. Two is that it should be multiplicative with respect to compositions. So if I have a composition of two embeddings and I plug that into mu, I just get the product of the two numbers. And then the third condition is the one that's a little more interesting, and it involves these amalgamations. So given kind of one of these amalgamation situations, we're going to list out all the amalgamations. So let say y prime alpha, I prime alpha, j prime alpha for alpha between 1 and r, be the various amalgamations up to isomorphism. The condition is that the measure of this embedding I should be the sum of the measures of the I primes here. The sum of alpha from 1 to r, but mu of I.
So those are the amalgamations in F.
In F, yeah. Obviously, you should start with something in F as well.
How do you think about amalgamation?
You're just gluing things together.
Or to give a concrete example.
I'll give an example in a second. Yeah. Oh, it's fine. Actually, let me just give you an example now. So to kind of show you some of the flexibility. So let's think about graphs. They're just finite undirected graphs. And so let's say that we have a graph with two vertices and an edge between them, and then here we have this is our x, this is our y. And here we're adding a new vertex called 3, and then we have x prime, and maybe this is we're adding a new vertex with an edge, and that's called new vertex 4. Is this x prime? Okay, so in an amalgamation, the graph should have vertices labeled 1, 2, 3, and 4. There's no condition in the definition of amalgamation that the images have to be disjoint or that they have to only overlap or they're required to overlap. So you could have more identification. So what that means concretely is that the vertices are labeled 1, 2, 3, and 4, but the label 3 and 4 could fall in the same vertex. That's allowed. Okay. In this case, I think that can't happen for any amalgamation because 3 and 4 kind of look different relative to 1 and 2. But so the way that you would get amalgamations here is you'd have a graph with 4 vertices. And if you restrict to just looking at the vertices 1, 2, and 3, you have to see this picture. And if you restrict to the vertices 1, 2, 4, you have to see that picture. But you're not given any information about what's going on between 3 and 4. So you could have an edge there or not. Okay, so there's 2 amalgamations in this case. Okay, and if y were the same as x prime, like if you had an actual triangle here, then 3 and 4 could be the same in an amalgamation. You could have them identical. Yeah.
So could you say what it is the signature and the sets R alpha?
R alpha is just a subset, which we think of as a relation.
No, but I mean.
Here, sorry. So here we're doing graphs, and the signature is just 2. So there's a single binary relation, and it's just recording, is there an edge between 2 vertices or not?
Okay.
Yeah.
And X is just the vertex.
X is the vertex set, and then R1 is the edge set. Yeah. Is that okay?
Yeah.
Okay. Yeah. More questions? Yeah.
Could you tell us what equation 3 says about this example?
Oh, yeah. So here we have our I, and then here we have, so this would be y prime 1 and y prime 2. And the equation would just say that mu of this embedding is the sum of the mu's of these. So we have I prime 1 is the map from x prime into y prime 1, and similarly with I prime 2. And so that's the equation. Any more questions?
How unique is this measure?
Oh, it's not necessarily unique at all. Yeah. Yeah, the main problem is, well, one of the main problems is given a Frise class, figure out what all the measures are. There doesn't have to be a measure. We know examples where there are no measures. And then there are examples where there are continuous families of measures and everything. And hopefully you can see now that this is a pretty fun concrete problem. You pick a Frise class like graphs, and you can just start writing down these equations, right? So like for each embedding, you have an unknown, and then here we have our linear equations, and here we have some quadratic equations, and it's a very kind of explicit elementary thing. And you can just start trying to solve the equations, but it can be quite challenging to solve.
Where does this, and you're putting a measure on this thing comes from?
Why is it called measure?
I mean, what purpose? I mean, I don't know how to ask.
Why are we doing this?
Yeah, sorry.
This is like the key combinatorial data that we need to make our tensor categories.
Okay.
So in the second part of the talk, I'll explain how that works, and then maybe it'll make more sense why we're doing measures.
So if you have like a Tanaka category, it comes with a measure.
Kind of the other way around. If you have a measure, you can build some kind of tensor category.
I see.
Yeah, which is not always pre-Tanakian, but hopefully it will be.
But it's Tanakian is pre-Tanakian.
Tanakian, yeah, everything that's Tanakian is pre-Tanakian, and it's just more. Tanakian basically just means rep G. More questions? Okay, so let me give you the kind of first example.
Now he was asking, like, you can't reverse engineer it and get a measure if you have a.
Sometimes you can. So to say how that works involves some technical terms, but these categories that we construct always have a big supply of Étale algebras in them. And if you have a pre-Tanakian category that has a lot of Étale algebras, then by looking at like the dimensions of the Étale algebras, you'll cook up a measure. So for certain cases, you can reverse it. I can explain what that means in more detail later if you want, but let me just leave it at that for now. Okay, so let's do an example. So the easiest example is we can take our Frise class F to just be finite sets with no structure. So the signature is empty. So we just need to give a number for every embedding of finite sets. And if I have an embedding of finite sets, like a 3-element set into a 10-element set, I can do that in stages, right? I first go 3 to 4, 4 to 5, work my way up. And so by this equation 2, you just need to know the embeddings of n into n plus 1. You just need to know the measures there, and then you'll know everything. So it suffices to know. Let me call an the value of the measure when we embed n into n plus 1. So it's nice to know this for all n. Okay, and so when I say it suffices to know this, it's like we're kind of already making use of equation 2, right? And so kind of the constraints on these ANs are going to sort of come from equation 3. So we should think about what amalgamations are telling us here. And the situation to look at is when we have just n going into n plus 1 in two ways, or it's the same embedding, but just looking at this picture. So here we have in each embedding that we're adding like one new element to the set, which I guess the way I set it up, it's called n plus 1 in both cases. But we have kind of two copies of the number n plus 1. And in the amalgamation, they can either be the same or they could be different. And that's kind of the only choice. So there's two amalgamations. So yeah, like usual, we call this x and x prime. So one is n plus 1 going to n plus 1. So this is my x prime and this is my y prime 1. And the other is n plus 1 going to n plus 2. So here's x prime and here's y prime 2. And so our equation number 3 in this case says that mu of n going to n plus 1 is equal to mu going of n plus 1, n plus 1, plus mu of n plus 1 going to n plus 2. And this is what we called an, and this is what we called an plus 1. And the first condition in amalgamation is that mu of isomorphism is 1, and here we have an isomorphism, so this has to be 1. And so this is what the equation tells us here. Okay, so if we let T be the first A, A1, then AN is going to be T minus n plus 1. Just subtracting 1 every time we go up in an index. And so in particular, if you look at
Is equals 0 is not allowed?
oh, sorry, T is A0. That's what I want to say. Then it is. Yeah, thank you. That's good. Right. So if we look at just the measure of an object, so let me just say this over here. So measures are defined for embeddings, but if I have an object X, I can look at the measure of the empty set, empty object embedding into X. So I can assign a number to every object. And so in this case, this is going to be 0 going to n, and we break that up as 0 going to 1, 1 going to 2, and we get the product of these A's. And so this is this kind of falling factorial thing. So I guess what I've proven here is that if you have a measure, it has to have this form. We haven't really rigorously proved that this works, but it does.
I'm not sure that was there anything in the definition that said that you cannot have isomorphic objects in your class because
That you can't have
isomorphic because here you should have only one of every side, only one object of a given size.
That's right in this case, yeah. So what were you asking?
So it means you don't allow isomorphic objects, different objects.
Well, I mean, in this, I mean, mu of isomorphism is 1, and combined with 2, that says that isomorphic objects have the same embedding. Yeah, or even isomorphic embeddings have the same measure you can deduce from this.
Oh, okay.
Yeah, so you kind of only need to think about the isomorphism. Right, so the final answer in this case is that measures correspond to complex numbers. There's a 1-to-1 correspondence. Okay. So if you look at this equation here, it has some meaning to it, right? This is, if T were a large integer, this would be the number of embeddings of this n element set into a T element set. Right? So it sort of suggests that we're kind of counting embeddings. And you can turn that into an idea that works in some cases. So I want to tell you this kind of general way that you can take that observation and make a measure in certain cases. So let's say that, so I'm going to go to like a general Frise class now. And let's say that we have an object E in our Frise class. So we say that E is called homogeneous. If whenever you have two embeddings of X into E, they differ by an automorphism. Okay, so for example, with finite sets, every object is homogeneous. But that's very rare. Most Frise classes won't have that much symmetry. So let's say that we have a lot of homogeneous objects. So say that we have E1, E2, etc. homogeneous, such that every object embeds into all but finitely many of these. So this could actually, in most cases, this will be a chain where E1's embedding into E2, E2's embedding into E3, and so on. So such that every X embeds into all finitely. Okay, so this is the situation where this kind of counting embeddings thing will work. So I guess the precise statement I want to make is that we can make a measure. So I guess first let me say, when I defined measure here, I said it was complex valued, but obviously you can talk about measures valued in any ring. And here I'm going to use a more general ring. So we can define a measure so I need to tell you where an embedding goes. And this is going to be a tuple of things. And this is going to live in the ring where I take the product of all z's, the infinite product of z's, and I quotient out by the direct. So this is going to be a tuple of integers, and essentially we're allowed to ignore finitely many of them that get the same thing. And the way that this works is, so here I is my embedding of X into Y. And what is the AN? AN is the number of extensions. Well, let me say this. So to define AN, let's if we choose an embedding of X into EN, then AN is the number of extensions of this embedding to Y. You have X embedding into EN, X embedding into Y. We want to count the number of ways of extending our embedding of X. This is independent of this choice of embedding because EN is homogeneous. Any two embeddings of X will look the same. And so there's some well-defined number of extensions of this embedding to Y.
So here you use method with value in a ring which is not.
That's correct, yeah. So this is our kind of coefficient ring for the measure here. Okay, and it's just kind of easy to check just kind of formally from our assumptions that this does define a measure. And if you go back to the symmetric group case, the number of embeddings here, this AN is going to be some polynomial function of n. Like just imagine the case when X is empty. So then we're just, and EN is just like the n element set. So then we're just counting the embeddings of X into the n element set. And that's given by this formula. And so actually in that case, this measure is landing in a subring here. It's this landing in the subring of polynomial functions, right? You can think of these as functions on Z where you ignore finitely many points, and we're landing in the ring of polynomial functions. And that's actually what usually happens if you're in this situation. So you're actually just getting some polynomials which give you the measure. So the finite set case works here. Some other examples. So by the way, if you have these E's, this is called smoothly approximable. This condition here is called smoothly approximable. So you say that Frise class is smoothly approximable if you can find these E's, and that's a very constraining condition. So other examples. So if you take F to be finite dimensional FQ vector spaces, that's smoothly approximable because if you just think about an n-dimensional vector space, it will have this property if you're embedding subspaces. There's actually some subtleties here with thinking about these things as relational structures, but let me not get into that. And this also works if you put on forms. So you can also include like symmetric bilinear forms, alternating bilinear forms or Hermitian forms. And these examples kind of lead to the interpolation categories for GLNFQ, finite orthogonal groups and such. Deline actually pointed out an interesting thing that happens here for the orthogonal group, which is that there's really four kind of natural families of homogeneous structures to use, because you can use the even dimensional spaces or odd dimensional spaces, and they can either be split or not split. And so you kind of begin by getting four families, but it turns out that two of them are the same. So you get two one-parameter families of measures in this case, which is kind of interesting. And then you can also sort of make this work if F is the class of finite T groups. And yeah, you have to say a little more about how to actually think of this in terms of this point of view of relational structures, but there's a way to do it, and this does count as smoothly approximable. And so in model theory, they've studied this smoothly approximable condition a lot, and there's some kind of rough classification. I don't really understand the statement of the theorem, it's quite complicated, but the essential idea is that they're kind of all very closely related to either the symmetric group or one of these linear group cases. And I think that means that these kind of interpolation categories that kind of came up in Deline's work and some of Knopp's work, where you're taking sequences of finite groups and interpolating the representation categories, kind of any example, I mean, this sort of, yeah, it sort of suggests that those examples are kind of coming from this smoothly approximable case, and that they should all be related to just these kind of very classical situations. There's no precise theorem along these lines yet, but yeah, just kind of the idea. So I had initially hoped that if you take the Frisé class of finite graphs, that maybe you could build some kind of measure for it by counting embeddings into a large random graph. But that doesn't work, and sort of counting embeddings never works outside of this smoothly approximable case. And kind of, so once you leave this situation, measures become much more mysterious. And there's lots of cases where they exist, but you don't kind of have as good a reason for them existing. Okay, are there any questions?
So say you took the sequence of complete graphs?
Yeah.
Everything embeds? And...
No, because we have to use induced subgraph. Yeah.
Okay, thank you.
Yeah, so for the definition of embedding that I gave, the only subgraphs of the complete graph are other complete graphs. But you just take a subset of the vertices in the induced graph. Yeah.
In the P group cases, you just see what the EIs say what the EIs are.
It's some kind of free P groups. Kind of, you have to go to profinite things and use the free profinite P group and generators. It's a little bit, yeah, kind of leaves our setup a little bit.
Couldn't you could you relax the condition of embedding to say that I inverse of R alpha is it's injective on the R's as well, instead of just being.
You could certainly consider that. I don't think that leads to tensor categories. I think something will break along the way. All right, so I next want to tell you about a measure that doesn't come from this kind of counting thing. And actually, I think it's easiest to understand this from this oligomorphic group point of view. So now I'm going to have a little interlude of the measure discussion and tell you how these oligomorphic groups work. Okay. So if we have a Frisé class, what Frisé did was define this Frisé measure. Which I'm going to call omega. So let me tell you what this is. So omega is a countable structure. It has countably many elements of the same signature. Such that the substructures of omega are just the class F. So the finite substructures. Kind of ignoring isomorphism. So everything in F will embed into omega, and omega is just kind of built out of things from F. So it has this condition. And then the key property is it has this homogeneity, which is the same as the things that the E's had a second ago. Omega is homogeneous. And let me just recall the definition. This means that if we have embeddings I and J of some finite structure into omega, this X is living in F, then there exists an automorphism of our omega, such that J is G. Okay, so let me just say a few examples. So if F is just finite sets, then this omega will just be just an infinite, countably infinite set. And it's always going to be important for us to think of the automorphism group of omega. This homogeneity condition tells us that there are lots and lots of automorphisms. So this is going to be an important group. This is going to be our oligomorphic group, by the way. And so in this case, this oligomorphic group G is just the infinite symmetric group. Another example is if we take F to be finite totally ordered sets. Then omega is just a countable totally ordered set that is dense. So you can take it to be Q with the usual order. And these precise limits are unique up to isomorphism. And in this particular case, the uniqueness is actually a theorem of Cantor that any two countable dense total orders are isomorphic. That uses this back and forth argument, which I think Cantor came up with, and that's actually really important in this whole theory. And so here, this group G is just the bijections from Q to Q that are order preserving. That's a very interesting group. And then just one more example, if we take F to be the class of graphs, just finite graphs, then this limiting object is this thing called the Rado graph. This is a graph on a countable vertex set, which is highly symmetrical. I think it first came up in random graph theory. If you take a countable vertex set and you connect every pair of vertices with probability 1/2, with probability 1, you get this graph. And you can see that this homogeneity condition, like if you take X to be just a single point, this is saying that any 2 points are off by an automorphism. So the Rado graph is vertex transitive. If you take X to be an edge, you get edge transitivity. But then you also get transitivity for just like every finite configuration inside of there. So it's very, very, very transitive.
Can you say briefly what S infinity is?
So I'm taking it to just be all permutations of this set.
All bijections.
All bijections, yeah.
Not the co-runner.
No, you can also use that, and it doesn't really make much difference for what we do.
But then why is it unique?
The omega is unique. If you have two countable sets that are in bijection of each other.
Thank you.
That's what uniqueness means. Yeah. Yeah.
I'm a bit puzzled. I mean, if you take a random graph on a countable and you do this G and 1/2, why do you have any automorphisms? I mean, why
do you get automorphisms?
Automorphism? Yeah, I would expect you to have none.
Well, yeah, it's surprising, right? Because a finite graph, if you take a random finite graph, it has no automorphisms. It's just different in the infinite case. Like the way that you build these automorphisms is you tend to build them up piece by piece. So it's like if you have a vertex and another vertex and you want to build an automorphism, you say this one goes to that, and then you pick another vertex and you want to extend your automorphism. And there's either an edge or there's not an edge. And in either case, there's certainly going to be something that looks like that. And so you can extend. And so there's kind of just never any obstruction to extending partially defined automorphisms. And that's why it has them. Yeah. Okay. So I really want to tell you what measures look like from this group point of view. If we have one of our structures X, I'm going to write omega like bracket X like this for the set of embeddings of X into omega. And the group G, the automorphism group of omega, acts on this because it's acting on omega. And the homogeneity condition exactly says that this is a transitive action. And in fact, the transitive sets that you see in this way are exactly the orbits that you see on Cartesian powers to omega. G sets of this form. Or is it so much? Okay, and if we have an embedding of like x into y, if I then have an embedding of y into omega, I can restrict and get an embedding of x into omega. So there's going to be a map of G sets in the opposite direction. And amalgamations mean something very nice here. So let's say that we have our usual situation, x going into y, x going into x prime, and then we label the amalgamations. So when I kind of do this omega construction, the arrows reverse. And so I have this transitive set omega x, and these maps to this. And it turns out that the amalgamations are telling you what the fiber product is. The fiber product is just the disjoint union of the sets corresponding to these y's. And this is easy to see, like if you imagine you have this amalgamation situation, so an element of the fiber product, that's an embedding of y into omega together with an embedding of x prime into omega, such that the embeddings agree on x. And so if you take the joint images of the embeddings for y and x prime, that image inside of omega will be an amalgamation. And so something in the fiber product is really like an amalgamation together with an embedding of it to omega, and see what makes the goodness. Okay, and so let's say what measure means from this kind of G set point of view now. So let me just make a new definition. So a measure for our G comma omega. Oh, sorry. There's one more thing I want to say over here before I go on, which is important. If we look at n element subsets of omega, so G acts on this set of n element subsets, and if we look at the orbits, by these conditions on omega, this is exactly giving us the n element structures in F up to isomorphism. Right? Every n element structure embeds, and so it gives us an n element subset, and any two embeddings of the same structure are off by an element of G. And in particular, this tells us that the G orbits on this set is a finite set. There's a finitely many orbits. And that actually implies that the orbits on the Cartesian power are finite as well. And this is the oligomorphic condition. So an oligomorphic group is just the permutation group that has finitely many orbits on every Cartesian power.
Did they all arise from this construction?
They all come from this construction, yeah. Okay, so in this second definition of measure, it will work for just abstractly any oligomorphic group, but you can also have in your head just the case discussed here, the one coming from this recital. So measure this is a rule. And it's supposed to assign to every, say, B to A, this is going to be a map of transitive G sets, a number. Here, yeah, let me just say this in words. So whenever I say G set, I'm going to mean G sets that like occur inside of powers of omega, so like the relevant ones. And so these are supposed to be transitive G sets. So really orbits on powers, orbits and powers of omega. So you're supposed to have a number to every map of transitive G sets such that some conditions like this hold. So one is, again, that mu of an isomorphism is 1. 2 is that composition works in the right way. And now this amalgamation condition actually becomes a little bit nicer. If we have B mapping to A and A prime mapping to A, we just look at the fiber products. So here's F and here's that prime. And the condition is now just that we can write it in this way, mu of F is equal to mu of F prime. So mu of f prime is not necessarily defined a priori, right? Because this b prime is not going to be transitive. If a prime, a, and b are transitive G sets, the fiber product doesn't have to be transitive. But what I mean by mu of f prime is I decompose this into orbits and then I just add up the values on each orbit. And from this point of view, the definition of, so yeah, like if you're just kind of given an oligomorphic group, it maybe is a lot more complicated to try to compute measures from this point of view because you don't have just finite combinatorial things now. But the intuition here is actually much more clearer than in that case. Like these equations probably don't mean anything to you, but it's kind of easy to imagine a meaning for these equations. It's really just saying that mu of f is supposed to be kind of like the size of the fiber of f. If I have a composition, the size of the fiber multiplies, and if I do a fiber product, the fiber doesn't change. So the size of the fiber should be the same. So a measure is kind of just a formal way of assigning a size of fiber to maps of transitive G sets.
Is that pretty much what I call the degree function?
Yes. It's just applied in a slightly different way. Yeah, I think yours are not necessarily applied to maps of transitive G sets, but maps that might have more than one orbit, and you kind of insist that on each orbit it has the same value, and that's why the degree functions are a little more restrictive. But it's very similar. Any other questions? All right, so let me just tell you about the measures on the totally ordered sets, and then we'll take a break after that. So that is going to be finite totally ordered sets. So the Frisé limit in this case is Q as a totally ordered set. You can actually use R as a totally ordered set. It's technically not the Frisé limit because it's uncountable, but it's going to be a little more clear. So I'm going to take omega to just the real numbers. So our group is just automorphisms of the reals that preserve the total order. And so given a finite totally ordered set n, we get this thing, this space of embeddings of n into omega. And I'm actually going to use a slightly different notation for that. I'm going to use parentheses instead of brackets. And so this just means the embeddings of n into R. And concretely what that is, it's just you're giving n points in the real numbers, which are in order. Okay, and so let me tell you a measure. So if I have, so this n to m is supposed to be an injection of totally ordered sets. It gives you a map the opposite ways on the R's where you're just forgetting some coordinates. And I'm supposed to tell you sort of the size of the fiber of that thing. And what you do is you just take the compactly supported Euler characteristic of the fiber. I see of the fiber of Rn. And this is a fancy way of saying -1 to the n plus f. Fiber of this map is not like a very interesting topological space. But the reason for saying it in this fancy way is that you can kind of just immediately verify these conditions from properties of the Euler characteristic. They're kind of, the properties of chi-c just kind of are built to give you exactly these conditions. So it works very beautifully. So you don't actually need to kind of go through the combinatorics of amalgamations or kind of think about anything to kind of prove that this is a measure. It just works. And in this case, there's actually 4 measures total. And the way that you get the other ones, it's just kind of a variant. You can take R and partially compactifying it by adding a point at plus infinity or at minus infinity. So there's 2 choices on each side, so 4 choices total. And then you can kind of do chi-c for those compactifications, and that gives you the 4 measures.
You're saying those are the only 4.
Those are the only 4, yeah. Yeah, so in this situation, this F is not one of these smoothly approximable things, right? Because every finite structure has trivial automorphism group, there's nothing homogeneous. So this is not coming from like counting embeddings, but we do have a nice conceptual description of these measures. So after the break, I'll tell you some more examples of measures. And I think in every other case, we basically don't have a conceptual description. We just get them by brute force solving equations. Okay, so any final questions before we break? Okay. Okay, thank you. So I actually want to say a few more examples of measures because I hope we haven't gotten to anything too surprising yet. And I want to tell you some of the weirder examples. And then I'll say a little bit about categories. A variant of this case is you can use cyclically ordered sets instead of totally ordered sets. It doesn't make a big difference. In that case, there's a single measure. But I want to talk about a slight variant of that case. So we can let F be finite n colored cyclically ordered sets. And this is a Frisset class, and I figured out what all the measures are. There's finitely many of them. And the measures are in bijective correspondence with directed trees with edges labeled 1 to n. And the number of such things is 2 to the n times n plus 1 to the n minus 2.
Direct tree means undirected graph of the tree, and then you direct the edges.
Exactly, yes. And yeah, this is one of these cases where I just kind of brute force solved the equations and found this. And I don't really have a good conceptual. I mean, the solutions of the equations really do canonically correspond to trees. It's not just that the numbers match up. So I have some understanding of how trees figure into the equations, but I don't have a conceptual way of like making the measure kind of directly given a tree. And I think this is, it shows that this idea of measure is really kind of combinatorially interesting. You can put colors on anything. And this example shows that if you color like these pretty simple objects, it changes measures quite drastically. And I don't really know what happens in other cases. So that's one thing. Here's a second variant. Instead of looking at a single total order, we can look at n just completely unrelated total orders. So it's finite sets with n total orders. Okay, so the n equals 1 case we were just talking about, there's 4 measures. N equals 2, the way you're supposed to think about this, the n equals 2 case, by the way, is a very classical thing in kind of combinatorics. They're called permutations or permutation patterns, because if you have a finite set with 2 total orders, you can enumerate your elements in order according to the first order. You have 1, 2, 3 up to n. And then under the second order, you're just putting some new order on 1 up to n. And so that's some permutation of 1 up to n. And these are thought of as kind of like permutation patterns because you're allowed to kind of go to substructures, which means you can like delete numbers from your permutation to get like sub things. And people like to think about like classes of permutations defined by excluding patterns. And there's all kinds of combinatorics here. It's very interesting. And that's for n equals 2. And then for n equals 3, they're kind of like higher dimensional permutations. They get much trickier to think about. So a theorem that I proved with my former graduate student, Ilya Nekrasov. We showed that in this case, let me call this f sub n. So there's always finitely many measures. And the number of measures we gave, the number of measures on Fn, we gave an upper bound. This is not the exact upper bound, but it's roughly e to the n squared log n. I have no idea how close this is to accurate. And I think I also cannot prove that the number of measures even goes to infinity or is even non-zero. No. I don't think I know how to do that. One thing that I do know is that for n equals 2, the number of measures on F2 is 37. So my student Ilya, he studied these measures in his PhD thesis, and he had this very nice way to get kind of, so that the equations for measures, this is an infinite system of equations and infinitely many variables. And he observed that in some cases, you can cut down the system to a finite system, which is great. And that applies in cases where you have like kind of totally ordered sets or trees or kind of linear structures in a way. And so the way that I did this was I just took his method and then I had to write some computer programs to actually write down the finite presentation. So I think in the end, there were 81 variables and 200 some equations. And then I asked Macaulay to solve the equations for me. And in the little paper that I wrote on this, there's a little note I wrote, and at the end, there's a table which has the 37 measures, and it tells you the values on kind of the basic embeddings you need to know. You only need to know the values on certain embeddings, and that determines everything. And the values are all +1, -1, or 0. And something that it's very interesting. It's saying that there's like 37 ways of assigning +1, -1, or 0 to an inclusion of permutations. And presumably there's some combinatorial meaning to these things, but I don't know what that is yet. I've just kind of brute force solved equations.
So it's enough to tell what's the embedding of empty set into something.
No, not empty set, but certain embeddings. Yeah.
So empty set to something, sometimes you will get 0.
Yeah, usually you get 0. Yeah. Yeah, actually something that's interesting is that if you have a measure, you can look at the objects where the measure is non-zero. That will actually be a Frisé subclass of your F. And in this case, you never get the full class, so things always vanish. But what's interesting here is for F2, Peter Cameron classified the Frisé subclasses here. And I think there's 7 of them, exactly 7 of them. And so each one of these measures has support on one of the 6 proper subclasses.
Sorry. Explain again just how this relates to the permutation pattern, like.
Yeah, so if I have a finite set with 2 total orders, let's say it has 4 elements, right? So I have order 1 and order 2. I guess I'll try to make it squiggly, right? So I can list the elements in ascending order for order 1, right? And then in order 2, these 4 things are put into a possibly different order. And so maybe it's like 3 is the smallest, and then 1, and then 2, and then 4, right? So this whole setup, you can just record by writing down the sequence 3, 1, 2. And we think of this as like a permutation of 1 up to 4. That's the idea.
So it's like a torsor for the symmetric group.
Yeah, that's right.
Does anything in your 37 and what you found the values on are distinguished permutations or patterns showing up there? Or am I misunderstanding the structure?
So these are rules that assign to an embedding of permutations in number. And like I said, they have support, and the support are defined by these kind of excluded pattern conditions.
Yes.
So they're sort of related, but I don't really have more to say than that.
But there's like some finite support, or there's some distinguished support.
And I wouldn't say that.
Okay.
Yeah, we can talk more after. Yeah.
Wait, is there a way to say this, what this number means in this case without using language measure?
Like what these 37.
Yeah, what does it mean?
I don't know what it means.
Oh, sorry.
I think that's a really important problem. Yeah. It would be very nice if someone could tell me a combinatorial meaning. Yeah. And then let me just say one more variant of this ordered case. Which is due to Sophie previously. So there's a linear analog of a totally ordered set. That's a finite dimensional vector space with a complete flag. So you can take F to be finite dimensional 2 vector spaces with a complete flag. And Sophie said, well, she found a measure. So there exists sort of a very nice measure in this case. I actually don't know. I don't know if you know the complete classification of measures. Okay, that might not be known, but this is certainly the best one, the one that she found.
Actually, the one that Professor Delane found is better.
So this measure leads to a nice tensor category, which is why I say it's very nice. So really what she was interested in was constructing the tensor category. Okay, so right, these are kind of all variants of finite totally ordered sets. Another class of examples comes from trees. If you take F to be trees, there's two one-parameter families of measures. It's an interesting story, but in the interest of time, let me just kind of skip that. I want to say one last example, which I think is really cool. So I guess this is 4. All right, so I've defined measures in this context of having this for Z class F. But if you think about it, like you can be more general than this, right? You just kind of need some notion of embedding and some idea of amalgamation. And if you're in a situation like that, then you can define measure. So it really kind of makes sense for a class of categories that kind of look like this. And in particular, you can apply this to the category of finite sets where the morphisms are surjections, and you take the opposite category. So I'll call that FS to top, FS is finite sets. So here an embedding of X into Y is really a surjection the opposite way. So if you think about an amalgamation, the situation that we start with is this. Right, so this is supposed to be like an embedding of X, that X prime is really a surjective function in the opposite direction. And so an amalgamation should be something that goes here, that maps down to each of those things. So in the classical situation where the orders were reversed, an amalgamation was jointly surjective. So here we want it to be jointly injective. And that means that it's just a subset of the fiber product. And then it should surject onto each factor because embeddings have to be surjections. So amalgamations correspond to subsets of the fiber product that surject onto each factor. Okay, and then you can, the definition of measure makes sense, and it's not too hard to figure that out. In this case, there are 2 measures. Okay. Well, what I really want to tell you is a variant expression. Let's fix a finite abelian group now. And now we're going to take F to be sort of the same thing. It's going to be finite sets and surjections, but we're going to put an M weighting on our set. So these are finite M weighted sets with kind of weight preserving surjections. So by M weighted, I just mean for every point in the set, you have an element of M. So weighting is just a function to M. And weight preserving means that if you have a surjection and you look at a point here, the total weight of the fiber should be the weight of the point. Okay, and if you think about it in a weighted surjection, the total weight of the set is not changing. So this category is kind of a disjoint union of categories where you fix the total weight. So let's just fix the total weight. So say a fixed total weight. Let me just call it chi. All right, so it's not too hard to show that measures are determined on some very small class of surjections. So if we're given alpha and beta in M, well, you would like to say, you can look at the surjection from the 2-element set down to the 1-element set. The 2 points are weighted alpha and beta, and then the thing that you're mapping to is weighted alpha times beta. And you would like to say that these are kind of determine everything. It's basically true, except here the total weight hasn't been fixed to our chi. So we just need to add one other point to adjust the total weight. So here I'm going to weight this as alpha chi times alpha inverse beta inverse, and here same thing. So if you know the measure of these surjections, you will know everything. Everything can be kind of broken down into compositions of these things, more or less. And so this means that a measure sort of corresponds to a function, which I'll call J. And it takes in 2 elements of our abelian group and gives us a complex number. And then you can translate the measure axioms into axioms here. And let me just tell you what the answer is. So such that, so first, it should be symmetrical. Second, if you make a slight modification of J, so I'm going to call it J star. And all you do is you subtract off delta A and delta B. So here, delta A is 1 if alpha is the identity element, and 0 if alpha is not the identity. Okay, so this is just J alpha beta, maybe -1 or maybe -2. And the condition is that J star should be a 2 cocycle. Okay, and actually it's J star that's really giving you the measure, and this 2 cocycle condition is kind of telling you that if you have a composition, then the measure multiplies when you compose. And then the third condition is what's going to correspond to the amalgamation equation. And if you think about trying to do an amalgamation here, like imagine you have this setup and another thing with 2 points mapping down to your 1 point here. When you do an amalgamation, you get this fiber product. So there's going to be 4 points in the fiber, because you're doing the product of the fibers essentially. And what's interesting is that you now get to choose how you weight those 4 points. And it just has to be kind of like, I don't know what the word is, a magic square or something, like when you sum the rows and you sum the columns, they have to be the things that you start with. And if you try to solve those equations in an abelian group, there's kind of one parameter of freedom. And so this is going to involve a sum over those one parameter of choices. And the equation is exactly this. If I sum over beta and m, and I do J alpha 1 beta, alpha 2 beta inverse, J alpha 3 beta, alpha 4 beta inverse. So this is like the sum of the amalgamations. This is supposed to equal J alpha 1 alpha 4 times J alpha 2 alpha 3. So it's not too hard to show that there's a bijection between measures and these functions change. What's a little bit harder is trying to understand what these J functions are. And what's very cool is the basic example comes from Jacobi sums. So if I take M to be the group of multiplicative characters of a finite field, with the homomorphisms of FQ star into C star, then if I do this Jacobi sum, so the Jacobi sum is, I have 2 multiplicative characters, alpha and beta, and I sum over elements of the field that add up to 1, which are both non-zero, of alpha x beta y. This satisfies the axioms. And the theorem is that these are the only ones. As long as M is non-trivial. So M is not trivial. These are the only examples.
The meaning M must be like the units in a.
Yes, so corollary is if a measure exists, M is cyclic, and its order is 1 less than a prime power. And this is the first kind of natural infinite kind of sequences of examples where there are no measures, right? So if you just look at groups that are not of this form, you get a whole big family where there are no measures on any of them. So with this theorem, the kind of more precise statement of this theorem is that if you have a J on an M, if you look at the Pontryagin dual of M, and you add 1 point called 0, there's a unique field structure on that set, such that the J that you were given turns into the Jacobi sum. So it's very cool. It's like the measure axioms are somehow like, it's sort of like doing the multiplicative Fourier transform of the axioms of addition for a finite field. When M is the trivial group, that's this previous example I said, where there's no weighting. And then there's 2 measures. And so one of them is like the Jacobi sum for the finite field with 2 elements. And the other one you can sort of think of as corresponding to the Boolean semi-ring. Okay, any questions? All right, so I'll now tell you a little bit about tensor categories. I don't really want to say too much, but I do want to say just So first, let me tell you how we construct tensor categories. So it's the basic idea. And for this, let me motivate this by first going back to finite groups. So if G is a finite group, we can define, well, you can think about permutation representations of G. They're the easiest representations. So permutation representation is one where the basis is just permuted by G. And so you can think about the category of permutation representations. And you can define this category kind of abstractly or directly. So the objects are or correspond to finite G sets. Let me call, I have a finite G set A. Let me call the corresponding object vec sub A. So it's like column vectors indexed by A. And then a map from vec A to vec B. Well, vec A is just the vector space with basis A. Vec B is the vector space with basis B. So if you're giving a linear map between vector spaces with bases, that's a matrix. So there should be a B by A matrix. And we want it to be a map of representations, which means it should be invariant. This is a G invariant E by A matrix. And then finally, composition is just matrix multiplication. Okay, and so we can just mimic this in the oligomorphic case. So given G oligomorphic with a measure mu, we can define some category of kind of permutation modules. So it's not literally a category of permutation modules, but that's the idea. And it's just kind of in the same way. So the objects are vec A, where A is a G set. And here by G set, I'm using the same convention as over here. So it's a finite union of orbits on powers of omega. A map from vec A to vec B is a G invariant function from B times A with the complex numbers. So think of that as like a B times A matrix. And then composition is like matrix multiplication, but B and A are infinite sets. So if you actually think of them as infinite matrices, you get infinite sums showing up, but the measure comes in to kind of save the day there. So composition, so given, let's say we have a matrix P from B times A to C, and then a matrix psi from C times B to C. We want to compose these two matrices. And what you do is you look at C times B times A, mapping down to C times A. And you just want to take the push forward of kind of the product function. So up here you have the function zyx maps to psi of zy times phi of yx. And we just want to push forward this function, right? Because that's, if you think about a z comma x here, the value of the push forward is the sum over all choices of y, and that's the formula for matrix multiplication. So I just need to tell you how to push forward functions. So, the composition is push forward. And so let me just tell you kind of abstractly how to push forward. So if I have a function like this, which is G invariant, and I want to push it forward, I need to tell you its value on some orbit. Let's say that we have a G orbit here. And I'm going to look at its inverse, the inverse image of this G orbit. And so there's going to be a bunch of G orbits up here. Let's call them E1 and En. So these are mapping down to pi. And so what you're supposed to do is you're supposed to, if you want the value of the push forward here, you're supposed to sum the values here. And the value of the function up here, since it's G invariant, takes the same value on each E. And so you just do the value of F on E times the measure. Okay. And this gives you a well-defined category. And then it has a tensor product. On objects, when you tensor vec A and vec B, you get vec A times B. And on matrices, this is giving you like a Kronecker product of matrices. And you have to go through the whole, tensor category definition, which is very involved to kind of, check all the details, but it all works. And so this is our category. And this is not one of these pre-Tanakian categories, because this is not an abelian category. This is just an additive category. So you would like to modify this to get an abelian category. And there's some cases where that's very easy. Some cases where you can do it and it's less easy. And then there are cases where we just don't understand what's going on at all. So let me write down a theorem at least. So whenever you have a tensor category, even just an additive one like this, there's a way to formally define the trace of an endomorphism. So if I have a map from M to N, from M to itself, I can look at the unit object of the category. And that maps to M tensor M dual. And then I can apply F on the first factor. And then I can pair the two objects back to the unit. And in these categories, the endomorphisms of the unit are just scalars. So this composition is just a scalar number. And that's called the trace. Traces always make sense in tensor categories.
You would say your objects are self.
Oh, that's a good point. Yeah, the objects in this perm category, like permutation representations, are self. So there are maps from vec A, tensor vec A to vec A, and the opposite direction. And these are kind of just coming from the map of G sets of A and A times A, which is the diagonal. Okay, so if you, I haven't really defined, pre-Tanakian categories carefully, but if you just kind of imagine some abelian world where this kind of thing makes sense, if you have a nilpotent endomorphism and you're in an abelian case, you can kind of filter your object such that on the associated graded, the map is 0. Because that's what it kind of means to be nilpotent. And going to an associated graded is compatible with traces. So if you're in an abelian case, nilpotent endomorphisms have to have trace 0. And that's kind of one of the main obstructions to like embedding a non-abelian category into an abelian tensor category. You need trace of nilpotent to be 0. And so so one theorem is that if that happens, so if trace of any nilpotent endomorphism is 0, and our measure is what we call regular. And that just means that it's always not 0. So U of I is not 0 for all I. Then, if you take the Karoubi envelope of this category, which means you just formally adjoin summands of objects, that's a semi-simple abelian. Okay, and we actually give a theorem in our paper, or a way of kind of checking this trace of nilpotent equals 0. This is kind of a big deal in tensor category world, checking that nilpotents have trace 0. And we give kind of a nice way of checking this in some cases, which was kind of a new criterion, which is pretty useful to apply this theorem. Okay, so this is, so basically you want this regular condition if you want a semi-simple category. There's relaxations to get categories that aren't semi-simple, but I'm not going to get into that now. So if you apply this in the case of the class, so if you take the for sake class to be finite sets, so the oligomorphic group there is S infinity. This kind of goes back to our construction recovers the category rep ST, but delete first of. And I just want to tell you about one other example, which is when we use finite trivially ordered sets. So here we can take G to be this automorphisms of R that preserve the order. And the measure that we choose here was this compactly supported Euler characteristic measure. Of course, in this previous example, I didn't say the measure, but it's the measure corresponding to T. And so I wrote the formula for this measure. It's always -1 to the n plus m, so it's always non-zero in this regular case. And our criterion applies and trace of nilpotent to 0. So we get a semi-simple category. Let me call this C. So C is the Ruby envelope of this term category in this case. And this is a semi-simple Reed-Knockian category. And this category is super, super cool. Like, and all the work Nate and I have done on tensor categories, this is clearly like the best thing to come out of it. It's just an amazing category. We call this the Delanoy category. And then Nate and I kind of defined this in our first paper together, but the real properties of this category were worked out in joint work with Noah Snyder. Okay, so it's a semi-simple abelian category. That's true in every characteristic. If you know anything about representation theory, that's crazy, right? Like characteristic 2, characteristic 3, always semi-simple. It's just amazing. Let me tell you some more properties.
Well, where does the characteristic enter into it? I mean, I don't need to see any characteristics.
Yeah, sorry, that was not clear. So when I defined measures, I used C, but you could use any ring. So this measure, the values are always plus or minus 1, so it's actually valued in Z, and then you can reduce mod P, and it always works. And that theorem works in characteristic P as well. Yeah. It's often just very hard to find regular measures in characteristic P. That's usually not going to happen. So here are some properties of this Delanoy category. So the simples are indexed by words in a 2-element alphabet. So I'll call a word lambda, and the corresponding symbol I'll call L lambda. Whenever you have a tensor category, you can define the categorical dimension of an object. It's just the trace of the identity map on that object. And in this case, these simples all have dimension plus or minus 1. The sign is just determined by the length of the word. And that's, again, a very unusual property in a tensor category. Usually the dimensions are going to be a little more crazy than that. And then one more thing is that we have a rule for the tensor product. You know, whenever you're kind of doing representation theory, decomposing tensor products is a big deal. And in this case, we have a complete combinatorial description. And the interesting thing about it is that it's so simple. It's more or less a shuffle product of lambda and mu. You shuffle the words together, but you allow letters to collide. So it's like shuffles, but you allow collisions. And when two letters collide, there's some rules for what happens. So if the letters are the same and they collide, you just get that letter. But if they're opposite letters, then you have to put in every possibility. So they can cancel or become one letter or the other letter. And that's the description. And I think that's very cool because most tensor products are either like trivial, like you're tensoring one-dimensional things together and then it's very easy, or they're much more complicated, like the Little-Bridges syndrome. And this is kind of in a kind of intermediate zone of complexity that I don't really know other examples of. Any questions? All right, so I just want to say one last thing about this category. So I want to say something kind of concrete and algebraic. I want to describe for you the endomorphism rings in this category. So in these perm categories, the maps from vec A to vec B were these A by B matrices, G invariant A by B matrices. And that means that it has a basis given by the orbits on the G orbits on A times B. And if you think back to our kind of combinatorial situation, when you do a product of G sets, the orbits are like the amalgamations. So it's amalgamations over the empty object. And so in this case, if we look at so let me call the basic object. So we have our totally ordered set N. And then we get some object, let me call it Xn, corresponding to it in the Delanoy category. So this is like the vec object corresponding to here. And I want to describe for you the endomorphism ring of this object. I'll call AN. So AN has a basis indexed by the self-amalgamations of this set. Okay, so you take a total ordered set with n elements and another copy of it, and then you amalgamate. And so you're kind of shuffling the sets together, but collisions are also allowed. Right, so if I draw a picture here, like if n is 3, we could have, so I'll color the things, I guess, red and white. So we could have one point here, and then a white point, and then we could have a point that's like both colors. I guess I'll just draw that. So now I have 2 whites and 2 reds, and then maybe 1 white and 1 red, something like this. So this is a way that you can picture an amalgamation. Amalgamation is just a totally ordered set, and you've 2-colored it white and red, and the colors can overlap if you want. And there's another way, another combinatorial way to record this, which is a little bit nicer. And this is using these Delanoy paths, which is where the name comes from. So you start at the origin, and you're going to read this from left to right. Every time you see a red letter, you step horizontally to the right. Every time you see a white letter, you step up. And whenever you see a thing that's both colored, you step diagonally. Okay, so here we would go right and then up, and then diagonal, and then right and then up, and we get to point 3. And this is called a Delanoy path. So a Delanoy path in the plane is just a path composed of these basic steps, 1, 0, 0, 1, and 1, 1. The number of Delanoy paths is called the Delanoy number. It was some classical combinatorial quantity considered by Delanoy, and that's why we call it the Delanoy category, because the Delanoy numbers are giving us our dimensions of endomorphism algebras. So let me tell you how multiplication works in the algebra. We have a basis given by paths, and so I have to tell you how to multiply 2 paths. And this is going to be a sum of paths with some coefficients. And so I have to tell you how to figure out the coefficient. And here's the rule. So what you do is you consider, so now we're given P1, P2, and P3. We have these 3 fixed paths, and I have to tell you how to get this structure constant from it. So you consider the 3-dimensional Delanoy paths. Q. So by this, I mean, like, you're in 3 dimensions, and now you can do steps where the vectors are just 0, 1 vectors, right? So you can kind of go diagonally in the XY plane or diagonally in all 3 directions or whatever. And you want to look at the 3-dimensional Delanoy paths such that when you project to the XY axis, you get this one, to the YZ axis, that one, and to the XZ plane, you get that one. So it's such that the 3 projections are P1, P2, and P3. And in fact, there's at most one of these Q. And the structure constant is -1 to, well, the length of Q plus the length of P3 if Q exists, and 0 if not. So I think this is a very pretty diagram algebra, which I don't think had ever been considered before our work on the Delanoy category. And the fact that the Delanoy category is semi-simple means that this algebra is semi-simple. So it's a product of matrix algebras, and I can tell you exactly how it works. It's a product from I = 0 to n. And then you take a matrix algebra of dimension n choose I. And then you take 2 to the I copies of that. It's the decomposition into matrix algebras. And in fact, this works over Z. The definition of the algebra works over Z. So the free Z module, structure constants are -1 or 0 or whatever. And this will hold even if you put Z there. And we have so this decomposition is corresponding to some idempotents in the algebra. And sort of the top level ones, when I is equal to n, this is n choose n is 1. So we're getting just 1 by 1 matrix algebras. And we know the idempotents explicitly for those, but we haven't worked out the general formulas for the other idempotents. So I think a good project I might give to one of my grad students one day is to kind of prove all this directly from the diagrammatic definitions, which I think would be a fun thing to do. I will. Yeah.
Oh, you mentioned really briefly like the Boolean semifield showing up. Do you think this extends to general semifields, or do you really need the field condition in general?
I don't know yet. Yeah, you can do this kind of M-weighted thing I was talking about. You can do that when M is a commutative monoid instead of a finite group. And then I'm wondering if you might get semi-rings related to that monoid, but I don't know the full story. Yeah.
Do you have any, so I guess you mentioned, so like, of course, there's a Delanoy case where these measures, they're either plus or minus one, or they sometimes may be zero. And you also mentioned that's true for this F2. So do you have any intuition about what it says about the Freise class when it has like these measures which are valued in like plus minus one? And
Oh yeah, that's a good question. So if you have a measure that gives you a tensor category, and your measure is valued in a finite and characteristic P, it actually has to be valued in the prime field. So that's one thing. So kind of if you want tensor categories in characteristic P, you only need to think about like F2 or FP valued measures, not more general fields. And F2 valued measures are very easy to understand. Well, if you want regular. So this theorem I wrote down said that if you want to get a semi-simple tensor category, your measure needs to be regular, nowhere zero. And nowhere zero things valued in F2 are quite easy. They always have to take the value 1. And so then the condition is just this amalgamation equation. Everything there is 1. You get 1 on both sides. 1 is a sum of 1s. And so the condition is just that there's always an odd number of amalgamations. So it's a super combinatorial thing. So I think like finding semi-simple tensor categories in characteristic 2 is closely related to just finding Freise classes with this oddness property, which is a purely combinatorial problem. And I don't know if anyone has any idea about that yet. Yeah.
We cast the classical Littlewood-Richardson story into this framework.
Well, I guess the Littlewood-Richardson coefficients are the tensor product coefficients for GLN. And well, there is an interpolation category for GLN, an algebraic version of GL. It's not quite this category. Anyway, I would say not really.
There's a shuffle, sort of the Plactic monoid, the shuffle kind of shuffle rule.
For Littlewood-Richardson?
Yeah.
Okay, I don't know that very well. I don't know how it would fit into here. We can talk about it more later if you want. Yeah.
So how often by this construction do you get a pre-Tanakian category which doesn't contain any non-trivial proper pre-Tanakian subcategory?
I think if you had a proper pre-Tanakian subcategory, kind of the philosophy, the way that you should look for those is as quotient groups, right?
Yeah.
Like some normal subgroup acting trivially. I don't think that is strictly always true, but that's, I think, the idea. And these groups like R, I think, are simple or very close to being simple. So I think in the examples we have, it doesn't happen very much.
But in like all these colored examples, you can have like a category generated by an object of one color.
That's true. And so those are the cases where it does happen. Those cases, when you have more than one color, I'm pretty sure you're not going to get a pre-Tanakian category though, although I don't know how to prove that yet. That's an open problem.
There are no more questions. Let's thank Andrew.